Okay, so I think it's time here to get started. So first of all, thank you so much, everyone here, for coming to my session. Both of you are here live, and also you who are looking at this from a distance. So my name is Silfvernagel. I work as a manager for AI and big data for Miles, a Norwegian consultancy company. And today I'm going to be talking about WebAssembly, and more specifically, how can you use WebAssembly in your front-end projects as web developers. So what we're going to do here today is we're going to have a small test example. How can we compile down to WebAssembly using Rust? And then we'll create an NPM package, and we will upload it to NPM, and then we will use it in a standard web application. And this will form sort of the basis for how you can extend this and use WebAssembly here. So there are more people coming in here. So there are some seats available here in the front too if you want to have a seat. So this is the agenda for today. So first I will describe the background of WebAssembly, and then we'll actually write our first Hello Wasp program. Then I'm going to give you an introduction to Rust as a language, and then we'll start this example here. How can we actually compile down Rust down to WebAssembly? We'll have a look at a game called Game of Life, and we'll also talk about performance, because performance is quite a big deal here when we talk about WebAssembly. We will have some real-world examples and also go into some of the future plans for WebAssembly. And we'll also cover some of the other frameworks, because there are actually quite a lot of different frameworks that are using WebAssembly in the backend. And then we have maybe a cryptic title here, New Old, so you will just have to watch and see what that contains. And we'll finish up with some conclusions and some references. But before we start with that, I just want to say a couple of words here about myself. So as I said, I work as a manager for AI and big data at Miles. And I'm also quite involved here in the local Norwegian community here in Oslo. So I'm part of the Norwegian.net user group. I'm also part of Oslo AI, which is an AI-focused user group. I'm part of a Swedish user group called the Azure User Group Sweden. And I also run an online AI school called AI42. So I'm going to say a couple of more words about that in the end if I have some time. So I'm running the AI42 school together with two of my MVP colleagues, eParty and GoShab or Seka. I'm also a Microsoft MVP and a Microsoft Certified Trainer. And if you want to get hold of me after this talk, you can find all of my social media handles on this slide. But first up here is what is actually WebAssembly. So first I would like to just ask the audience here, how many of you have tried out WebAssembly before? If you could raise a hand. Okay, yeah, so it's not super many. So I think this could be a very valuable talk for you here. So WebAssembly came to life in 2015. So it was a group that was formed by all the major browser vendors. And there was a release in 2017. And the first W3C public draft was published in 2018. And by December 2019, it has been a W3C recommendation. And what that means is that it stands on the same grounds as HTML and CSS and JavaScript. So you can say that this is sort of a standard tool in a web developer's toolbox. And it's also supported by all the major browser vendors, both in the desktop but also in the mobile version of their browsers. So that could also be good to know. So if we want to contrast JavaScript with WebAssembly, we can say that JavaScript is a high-level language. It's quite flexible and expressive. It's also dynamically typed. You don't need to compile it. And as we all know, it has a huge ecosystem that you can make use of when you build your applications. Whereas WebAssembly is much more of a low-level assembly-like language. And it has a compact binary format. And what it does is it promises us near-native performance. That's sort of one of the main benefits why you should be considering WebAssembly is if you want to have something where you need to have your calculations running very fast. Like it could be a graphical engine, or it could be a mathematical calculations or something like that. So the way that we work with WebAssembly, we can write WebAssembly right out just using an editor, but we don't really want to do that. That will be obvious here in a couple of slides here. But what we much rather would like to do is like to use a high-level language like C or C++ or Rust or Go, and then we want to be able to compile down these languages down to WebAssembly and then use that as a binary format in our applications. And actually, as of now, there are around 40 different programming languages that we can compile down to WebAssembly. So this is an image that is taken from a blog series by Lynn Clark. And what this image is trying to explain here is that usually what we have is we have a high-level language like C or C++, and then we take this high-level language and we translate it to an intermediate representation, which in this image is called IR. And then there's another part of the compiler that will compile this down to a target architecture, which is usually either the x86 architecture or an ARM architecture. But now when we're using WebAssembly, sort of the problem here is that now we will have code that will be executed over the web. So that means that we don't really know beforehand what is the target architecture that we want our code to run on. So we can say that WebAssembly is like a machine language here for a conceptual machine. So what we do is we write down WebAssembly instructions, which we can call virtual instruction, and then the browser will download the WebAssembly, and then it will compile it down to the target architecture that the browser is running on. So also some more background here information about WASM. So it's based on a previous project called ASM.js. So that's part of the reason why we could get this into W3C standard so fast. So if you want to know more about that, I recommend you to look into the ASM.js project. But basically, it's an intermediate language, just as in similar fashion as Java compiles down to bytecode and C# compiles down to MSIL. And it's also a strongly typed language, but we have only 4 different types. We have the 32-bit integer, we have the 32-bit float, and then 64-bit integer and 64-bit float. So now when we sort of know the basics about WebAssembly, then it's time for us to actually write our own first Hello Wasm program. But there is actually a caveat here, because the thing is that, as maybe some of you noticed in my previous slide, we don't really have string or char as a type in WebAssembly. So that means that it can be quite cumbersome to write this Hello World program. So instead of writing a Hello World program, what we usually do is we write a mathematical expression instead, so that we can make use of this integer and float types that we have. So what we're going to be writing here is an add WebAssembly program here. So in WebAssembly, we have 2 different types here. We have WAT, WebAssembly textual format, and then we can also parse it down to binary format. So if we have a look here at the textual format here, we first need to define a module, and then we define a function inside that module. So in this case, we define a function called add2 that takes 2 input parameters, 2 32-bit integers, and then it will output a result, which is also a 32-bit integer. And then you can, so WebAssembly is a stack-based language, so you can use get local on the input numbers, and then you can use a mathematical operation here. So in this case, we use the add operation. So WebAssembly supports something like 60 or 70 different operations that you can use. And then after that, we need to define what will the result actually be. So we need to use the export keyword, and then we export our function as the add2 function, and it points to this function that is called add2. And there's also a tool here called what2wasm. So with this tool, we can parse between this textual format that we were looking at before, and then we can write it down to the binary format. And we can also write this binary format out to a text file or out to the standard out. And that's what we've done here. So as we can all see here, this is an assembly-like language. This is basically what it will look like in the textual instructions here. But then if we want to use our WebAssembly module here, the first thing that we need to do from a web application, so the first thing that we need to do is we need to fetch our binary file. So that is this add.wasm. So we do fetch on that, and we read it into an array buffer. And then after that, we can instantiate the WebAssembly. Since that is a part of a standard, we don't really need to do anything else than just call WebAssembly.instantiate. And then after that, we can assign we can assign an object that we call add2, and we assign that to this function that's been exported by the WebAssembly. And then we can just call this function with 2 input parameters. And then we will have the resulting function out using the alert function here. So then we just get 4 here when we added the 2 plus 2. So that's sort of our hello world example here in WebAssembly. Then another tool that could be interesting to know about is something called the WASP Code Explorer. So what you can do with the WASP Code Explorer is if you have a binary WebAssembly file, then you can just drag it into the WASP Code Explorer and you can get the textual representation back. Because as we mentioned before, it's just sort of a parsing here between the textual representation and the binary representation, so we can switch back and forth between these 2 representations. This can be a good, useful tool if you have a WASM binary file and you would like to know what does this actually do without having to run it. So now when we talked a little bit here about WebAssembly and we run our first Hello World program in WebAssembly, we're going to have a look at Rust. Because what we want to ultimately be able to do is we would like to be able to compile a Rust program down to WebAssembly, and then we would like to make an npm package and then use that npm package in our own web application. So some background about Rust. Rust is a system program language from Mozilla. It has a syntax which is very similar to C and C++. It's strongly typed, and it compiles down to native code, so you don't need any virtual machine, for example. And one of the design criteria when they created the Rust language was that Rust should be a memory-safe language. So that means that you will have no dangling pointers or no memory exceptions or anything like that. So it's a very stable language to use. And in Rust, we also have a tool chain with some tools that we need to know about. So the first tool here is called RustUp. So RustUp is basically the installer for Rust. And then the second is Cargo. So in Rust, similar to npm, we have a package manager. So Cargo is the Rust package manager. And in Rust, we call these packages, we call that for crates. So there is also a site called crates.io where we can store all these different crates that we have created. And here's an example here of how we can write a Hello World program in Rust. So we define our main function, and we define that we want to print out a line here, Hello World, and then we can use Rust compile, and we compile our language, and then on a Windows machine it will generate an exe file, and then it will just print out a Hello World here on the command line. But we can also use a cargo to create like a template for our program. So if we run cargo new and then the name of our program, it will create a binary application here and a package structure. So we can see here, if we open up the main Rust file, we can enter that it should print out the Hello World program again. And then we also get a TOML file, which is like a package description of the package that we have here. And we need to, at the minimum, we need to define the package name, the version, and also the authors, and also any dependencies that we have. So we're going to be talking a little bit more about these dependencies that we can have on other crates. And in order for us to run this, we just run cargo run, and then it will compile our Hello World program. And then after that, it will run. So on a Windows system, again, it will produce an exe file that will run here. And we also have some types here in Rust. So we both have what they call primitive types, which could be integer and float or Boolean. And then we have something that they call primitive constructs. So these are more like containers, like arrays or pointers or tuples. So now how do we actually do here if we want to be able to compile our Rust program to WASM and use it in our web application? So the first thing that we need to do is we need to install this Rust toolchain that we were looking at, the RustUp, the cargo, and the Rust compiler. And then after that, we can install a package called wasmpack. And what this package do is that it will compile our code down to WebAssembly, and it will also install a package called WASM-bindgen. And this WASM-bindgen package, what that does is generates something that we can call a glue code, so that we can call JavaScript functions between Rust, to and from Rust, and also from WebAssembly. So we'll have a look at this glue file or glue code here in a short while here. So this is the result here. If we do that, we get again the package file or the TOML file where we have the package and the authors, and also we need to define what kind of cargo is this. So in this case, it's something called a CDI library or CDI lib. And we also need to define dependencies. So in this case, it's important that we have a dependency on this WASM-bindgen, so that we actually can be able to call this once it's been compiled down to the WebAssembly. So here we can have a look at the main Rust file here. So we need to mark up our Rust code here. So what we first define is that we want to use an external crate. So in this case, it's the WASM-bindgen that we want to be able to use. So again, this allows JavaScript both to call the Rust API and commercially. And then we can define here using the WASM-bindgen that we need to be able to use an external function. So in this case, we define the signature of this external function. So in this case, it's the JavaScript alert function. So we need only to define the signature for that, and then we will be able to call that from inside our Rust file. And then we have our actually public function here, which we call greet. So what it takes a name as an input parameters, and then we can use the alert function, which is again the standard JavaScript alert function. And then we can format it and print it out here on using alert. Then we can use again the WASM pack in order to build a package here that we can use in order to create an npm package. So we get the folder structure called pkg, and we will have a look at that short, what that contains. And then we can just do as we would do with any other regular npm package. We just use npm publish package, and then we will have our package up on npm. As we can see here, the hello wasm silver package that we've created here. So the contents of our contents of our folder here is first a TypeScript file. So in the TypeScript file, it defines what are the functions inside our Rust code that can be called from an external function. So that is what is the function that we can actually call from our JavaScript code. So in this case, it's the greet function that we will be able to call here. And then we have also this glue file. So that's why we have this WASM-bindgen. So here we can see the hello wasm silver.js. So what it does, it tries to call wasm.greet and pass the parameters down to wasm. And then we also have a package.json file with name and the version and the licenses and so on. And then we can use it just as we use any other package. We create a webpack config file where we define the entry point to our application. We create a package.json file where we define that we want to use this hello wasm silver npm package that we just created in our previous step. And then we can just create an HTML file where we refer to this index.js file. And the thing is that at least up till now, we can't really call it directly. We need to use an asynchronous call here in order to use this package here. So we can use js.greet and then whatever we want to be published here out on the alert. And then we get back our greetings here. So then we can have a look at a little bit more complicated application here using the same type of principles here, that we first create an application here in Rust, and then we compile it down to WebAssembly, and then we use it on the web here. So the example here is a game of life. So the game of life is sort of a simulation where you have a game board where you can have different cells, and then there are some different rules to this game. So the first rule is that any live cell with fewer than 2 neighbors will die because of underpopulation. And the second rule here is that any live cell with 2 or 3 live neighbors will go on to the next generation of our simulation. And also any live cell with more than 3 live neighbors will die because of overpopulation. And there's also the last rule is that any dead cell with exactly 3 live neighbors will become a live cell because of reproduction. So we can have a quick look at how this looks like. So now we can see we started the simulation, and these black boxes represent the cells, and then we can also pause our simulation. So we pause our simulation, then we can go into the board and manually add some cells that will affect our simulation. So we added a couple of cells here, and then we just continued our simulation. So the question is, how did we make this happen? So then it's very similar to our previous example that we were looking at. Again, we have this cargo toml file where we define what is the package, what type is it. So again, it's the same thing here. It's the cdylib package type, and what are the dependencies. And again, we also need to use this wasm bindgen in order to be able to generate this glue code so that we can actually call our WebAssembly from an external function. And this is the main Rust file. So in this file, we define our game plan that we call universe, what is the width and what is the height. And we also have some public getters and setters for our simulation. And we also have a toggle function. That's the function that we use when we were pausing our simulation, and we manually entered some cells into our simulation. And then we also have this TypeScript file, and similar to our previous example, this defines the different types of functions that an external function actually can call. So we can call the width and the height in order to get that. Then we can also call the toggle cell with some parameters in order to select or unselect a cell in our simulation. And then here we get, again, this sort of glue file. So we can see that, for example, if we call the toggle cell function, it will try to call wasm.universe toggle cell with the defined input parameters. And this is the way that we would use it in web applications. We define an index.html file with a bootstrap.js file, and we load this again asynchronously. And then after that, we can, for example, add some parameters to our simulation, and we can also define what is the event handler if we call this universe toggle cell, for example. So now that we have had a look at some initial applications and a little bit more complex application, we can talk here about performance. Because the main deal here is one of the good use cases with using WebAssembly is if you want to have something that runs fast. Like it could be a shader, for example, or it could be some complex mathematical operations, or it could be, a game or parts of a game. Then WebAssembly is a really great candidate, because what you can do is you can have the code running in C or C++ or something that runs very fast, and then you can use WebAssembly in order to be able to call that from your web application. And here there are some people who have done some tests here. So what they've done is they have run some calculations both in JavaScript, in Chrome, in Firefox, and in Safari. And then they've compared that to what is the similar execution time if you run the same thing in WebAssembly, in Chrome, in Firefox, and in Safari. And I think the most interesting thing with this graph here is the spread here. If you have a look at the JavaScript results here, you can see that there's quite high spread in this box plot. So that means that if you use JavaScript, you're not really guaranteed what kind of execution time you will have for your JavaScript functions. Whereas if you would be using the WebAssembly, you can see that the spread is much smaller than for the JavaScript functions. So that means that we can be much more safer, that we can have sort of a guaranteed execution time if we're using WebAssembly. And we should also take notice here that JavaScript has been around for quite a long time, so we've been able to do quite a lot of optimization for JavaScript in order to run, whereas WebAssembly is much more newer, so we can expect these differences to be even larger here with time. So now I'm going to present a couple of real-world applications. The first application is digital signal processing library. So this is one of sort of the prime examples of how you should be able to use WebAssembly. So some people that had the WebDSP language written in C++, and what they did was they used WebAssembly so that they could use this WebDSP on the web. So if I run this. So this is an example of some real-time performances here where you can do some image filtering in real time, both on images but also on real-time video. So I think this is a nice example on how you can use WebAssembly in order to be able to expose your applications to a much larger audience out on the web. Then another example is from AutoCAD. So AutoCAD, they have been around for quite a long time, so at least from the 70s. So they have lots of different building and construction drawings. The thing is that they would really like to be able to expose all of this information to the customers using the web. So I'm just going to take a little bit of water here. So the first thing that they started out with was actually in 2010. So they used, the primary technologies of that time, which was a Flash app. So they created an AutoCAD Flash app that they could use in order to expose this functionality on the web. Then after that, we fast forward a couple of years here to 2014, and then HTML5 and JavaScript had entered the scene. So they created a similar application for that. And then they were actually using this ASM.js project that we were talking about here in the beginning in 2016. And then they have their own format here for their drawings called Real DWG. So they were able to create a Real DWG-based viewer here in 2017. And then finally they launched a web app using WebAssembly. And we're going to have a quick look here at how the architecture is looking in order to do that. So the nice thing here about this is that they had lots of legacy code written in C and C++. So they could still use that, and they could still have the people who were maintaining all of that code and who had the domain knowledge about that. But then they created the middle layer, so they could compile this to WebAssembly and create like a WebAssembly middle layer, and then you could use any type of front-end library like React or Angular or Vue or whatever you would like to do it. So I think this is also an example of separate of concerns here. So that means that you're making use of the knowledge that you know best. So the C++ developers could still focus on the AutoCAD the core functionality, whereas the web developers can use the frameworks that they want to use and expose this functionality out on the web. So I'm also going to talk a little bit here about the future plans for WebAssembly. So maybe as some of you might have noticed here in my examples here is that we can't really use WebAssembly to call directly to the DOM or to the web API. We need to go through this glue code that I was showing you. And also in addition, we also always needed to load our WebAssembly asynchronously. But what we would ultimately like to do is they would just like to be able to import it just as any other package using import in JavaScript. So these are some of the next planned steps here for WebAssembly. Now over to something different here, because one of the things that could be very interesting for us to know about is something called serverless WebAssembly. So the WebAssembly is not only for the browser. So there are some providers like Cloudflare and Fastly that support WebAssembly. And why would we like to do this? So one of the reasons is that we would like to have faster launch times, or we don't need to rewrite some calculation engine over to JavaScript. And we'll also have much more lightweight applications because you don't need to do a lot of a lot of calculations here in your client. Like a schematic overview here is that we can see different kinds of use cases. Either you can have your calculations done traditionally on the back end, so you have a front end that just calls to the server side and retrieves its results back. Or you can do it all on the client side, so you can just use client side JavaScript and also do your calculations in JavaScript. Or in the third case, what you've done here is you've created, as we did similar, maybe we had the calculation engine written in C, so we compiled this C code down to WebAssembly, and then we use the WebAssembly in our web application. But this is still running on client side. Or the last example is the serverless WebAssembly. So what we do here is we call a serverless function that exposes WebAssembly functionality here to do some major data processing for us. And then we have some different options here. So either we can use a node for our serverless function, and then one thing that is also interesting to know that then we will pay a penalty here for initializing our serverless function. So the penalty using node runtime is around 200 milliseconds. But we also have some other alternatives. We have Fastly, so they have created something called the Fastly Terrarium, where they have their own runtime that they call Lucette. So with Lucette, you actually reduce this from the 200 milliseconds down to 35 microseconds, which is quite an improvement. So that could also be interesting to know. Or you can use a Cloudflare worker that runs on the V8 engine. And in this case, we reduce it down to 5 milliseconds. So, so these are some design choices that you can take as a developer, depending on how performant you need your system to be. But as I mentioned here before, that WebAssembly is not only made in order for us to be able to run things on the web. So there's also a standard called WASI, or the WebAssembly System Interface. So here the idea is that also, as we were talking about here in the beginning, WebAssembly should be able to run outside of the browser, and we can call the WebAssembly language as a language for a conceptual machine. So basically what we would like to have is an interface also for a conceptual operating system. And if we can make this happen, we will be able to run this for all operating systems. So again, this is also from Lynn Clark. So I recommend you to go more into this blog post if you want to know more. But usually what happens is you have some sort of function that will guard all the sensitive operations that the program might want to do, like, for example, accessing the hard drive. So by standard, WebAssembly runs under the same restriction as JavaScript. So you don't have full access to, for example, your file system or system programming functionality. But what you can imagine is that you have some sort of an interpreter or some sort of a middleman that can negotiate the things that WebAssembly would like to do to your file system. So I can check if do you have the right privileges for performing this operation, and is this sort of the right time in order to do that. And if that's the right time, it will just marshal that call further down the stack into the operating system. So this is a way that we can use WASI in order to access our file operation, for example. And you can find more information here on the WASI homepage here. And one thing is also that WASI runs in its own runtime called the WASM time. And a quick example of that is here we have a demonstration program here. So basically what we would like to do here, without going into the details, if we just would like to write a string down into memory. And in order to do that, we need to have access to our file system here. So the first thing that we can do is we can run this WAT file in the WASM time. So we just run WASM time with our WAT file, and we get the hello world. So first we write it to the file system, and then we take it back and print it out on the console. And then again, we can use this WAT to WASM in order to convert it or parse it over to our binary format. And then we can run our binary format, and then we get the hello world program back here. So that's a way that we can use it actually on without having to run it in the browser. So now I would like to demonstrate a couple of other frameworks that are also using the WASM. So one of them is an experimental framework called Pyodide. So the main objective here with Pyodide is that you would like to bring the Python runtime over to the browser, so that you can use, if you're a data scientist, you can use your standard libraries like NumPy or Pandas or Matplotlib and so on. So they're using WebAssembly in order to do that. So this is very promising because it's much easier to share and collaborate with other data scientists or machine learning engineers if you can just point them to an URL on the web instead of having to share your Jupyter notebook, for example. Then another example here that we have is something called assembly script. So what assembly script does, it compiles a subset of TypeScript to WebAssembly using a compiler called Binarin. And this could be an interesting project to have a look at, but it's also important to realize that that as opposed to WebAssembly, which is a standard, this is a much smaller project that has, some sponsors, but it's nothing like Mozilla or Google or anything like that. So that's something that you need to take into account. So you can see, for example, one of the things that we need to do here if we use assembly script, if we need to allocate our own memory, and we also need to be able to deallocate it once we're finished with the calculations or the things that we would like to do here with in our program. And then one sort of the prime examples here, one example that can be very interesting in this conference or in this setting is Blazor. So Blazor is a way that we can build our client web applications using C#. So there are two versions or two flavors of Blazor. One of them is running on the server. It works that you have client events that will be sent back using SignalR, or you can run it on WebAssembly. So then you will have .NET running on WebAssembly in your browser. And this was actually demonstrated or the ideas behind this was demonstrated the first time on this conference, on the NC conference in 2017. There was one of the Microsoft people, Steve Sanderson. He was demonstrating how you can use WebAssembly in order to do some factorial calculations. And then there were two different teams inside the Microsoft sphere. One was the Mono team. Mono was an open source project where they had converted or compiled the .NET runtime into a framework that you can actually use in WebAssembly. And then the other team was the ASP.NET team that took responsibility of this and tried to make it into a more commercial offering that we now know as Blazor. So a quick overview is that you have your CS file, your CS HTML file, and what you do is you compile this down to .NET assemblies. And then since we have this Mono framework, we can compile our code to WebAssembly, and then we can run a regular DLL that is using .NET functionality. We can run that in our browser. And if we want to have a look, so here's like a standard example where you have a counter. And then if we compile this, then we will finally have these things downloaded in our browser. So so it's not, at least this was quite spectacular at that time. So it's not every day that you can see like the Microsoft MS Core lib DLL running in the browser, for example. So if you haven't looked into Blazor, I would highly recommend you to do that. But then, as we all know, not every one of us are fond of C#, so there could also be some people that are much more interested in F#. Do we have any F# developers here in the room? Okay. So then maybe this is a slide for you then. So there's a framework called Bolero, and with Bolero you can actually write your WebAssembly. You can use F# in WebAssembly, and then you can run your F# programs on the web and develop single-page applications. So I'm not going to go so much into that, but for those who are interested, you can have a look at Bolero if you want to know how can you actually use a functional programming language like F# and write your applications and be able to expose this functionality out on the web. So now something that maybe many of you have wondered, what is this all about? So that's this new old headline that I was talking about. So the thing is here, have we not seen all of this before, that we should be able to run this on all sorts of different systems, and it should be supported by everything? Well, if we have a look back in history, we can think about the ActiveX components, or we can think about Flash, or we can also think, if we want to do that, or if we don't want to have nightmares, about Silverlight. But the main thing here is that there's a big difference between these three different previous attempts and WebAssembly. And the main difference here is that all of these previous technologies have been more or less proprietary systems. So they have not been part of a standard. Whereas now with WebAssembly, as we talked about here initially, it's actually part of the W3C standard. And it's also a recommendation in the same way as we have HTML, CSS, and JavaScript. So I think we can be pretty safe that this will not go away in the first time. So then, so what is the conclusion? Because the thing is that a couple of years ago, when WebAssembly was sort of first published or got a lot of notifications, was that a lot of people said that, now WebAssembly will kill JavaScript, so that all JavaScript developers will be out of the job. So the question is here, should we do WASM all the things? Well, according to me, we shouldn't be too worried about that. I think all of us who are working with JavaScript will still have a job here in the future. So I would say that WebAssembly is much more just another tool in your toolbox, which can be great for some specific scenarios. Like, for example, this scenario that we had, that we already have an existing code base in C or C++, and we want to be able to expose that kind of application or that sort of functionality out on the web. Or, as we have also seen here, if we have some sort of complex logic or some sort of calculations that we want to be able to perform fast, that we can run that, or we can write that code in C or C++ or something which is very performant, and then compile it down in WebAssembly, and then we can just use it on the web. So these are sort of, at least for now, that's sort of the main use cases for WebAssembly. I mean, we don't really know what the future will have in store, but I would say that these are sort of the scenarios that you should focus on if you want to consider WebAssembly. So then finally, I have some references here. So for those of you who want to know more about, for example, the service of WebAssembly, you can have a look at this. And there's also some great documentation both on the Mozilla website, and you can also have a look at this digital signal processing library that I was talking about. Or you can also have a look at Blazor, which I highly recommend for everyone else here in this room here. So with that said, I would like to thank all of you who came here to my presentation. And if you want to reach me, you can either reach me on Twitter, or you can reach me here on the email address here on this slide. But there are still some minutes left here, so I'm going to take this opportunity and just give some commercial here to this AI42 AI school that I was talking about. So this is community-driven initiative, which means that everything that we do is free for everyone, both the content and to be able to participate. Everything is written here. Everything is done voluntary. So the way that we do this is we would like to offer everyone around the world an opportunity to get into machine learning and data science. And the way that we've done this is we've compiled a curriculum where we start out both with the basics of mathematics, of probability theory and statistics, and then we go step by step over to using Python and using R and using tools like Databricks or Power BI, so that you ultimately will be able to create your own machine learning algorithm and be able to deploy it somewhere out here on the web. And we are streaming every second Wednesdays on both on YouTube and on Twitch and on Twitter and Facebook. So if you are interested in this, you can take a screenshot of this, or you can just scan these QR codes. So then we'll get both to our meetup page and also to our YouTube page where we have all the previous sessions that we have created. So with that, thank you so much for everyone for coming.